thank you all for coming to my talk about Windows, because I know a lot of you are not Windows people. I'm not either, but I have a client who uses Windows, and they have a problem. They have servers. This is actually one of their servers, but not one of the ones that's causing the problems. And these servers have local disks in them, which are actual spitting rust in a lot of them, but they're physical disks that contain secrets. And these machines, as I mentioned, run Windows. But Windows is not actually the problem either. The problem that they have is, where do the secrets that are on those disks go, say when they decommission them or when they transition them between different internal groups inside the company, or if they go back for service? That these sorts of secrets are valuable company data. And this isn't a hypothetical risk. There are lots of corporate disks that end up on eBay where people buy them and find all sorts of interesting secrets, personal identifiable information, medical stuff. So, you might be thinking, this sounds like a job for encryption. And you're right, but with encryption, just brings key management problems. So we need to do something about that. But before we can talk about the key management and how we deal with it, we have to talk a little bit about the boot process and where can we store secrets on commodity hardware. There's some stuff that happens during boot at the reset vector, and I've actually got another talk about that when I researched how bootguard worked, but we're going to skip all of that and just jump to the part where UEFI has been loaded from the SPI flash and has booted the computer. The first thing it does is find the EFI system partition, and it loads the Windows bootloader from it, the boot manager. And that then is able to unlock the BitLocker volume and start the Windows kernel, which of course then wants to do an update. Seriously, like every single time I start this computer, any of these Windows machines, they want to do an update. But where does BitLocker get the secrets from that it uses to unlock that volume? It has a whole bunch of what it calls protectors. These can be TPM sealed secrets. They can be user pins, or pins that the user types in, or they can be things like bulk encryption keys that are stored on removable media. And in general, the recommendation is to use the TPM sealed secrets, which is really nice if you want unattended booting, which in a server is frequently desirable. You want the machine to come up without someone having to toggle in the BitLocker pin on the front panel. The problem is that if the machine boots with in an unattended fashion, is that someone could boot the machine and perhaps sniff those TPM secrets as they go across the bus. In fact, they could do more than sniff the secrets. As we learned earlier today, they could do sort of active interposing and try to interfere with the process. So we have a lot of concerns around that, and we're actually trying to update all of our software to do encrypted sessions because of the physical attack concern. The other characteristic that we want is that we want the machines to only boot in this automated fashion if they're on our internal network. So that if somebody buys one of these machines off eBay somehow, or if it gets shipped accidentally to the wrong customer, we don't want it to automatically boot and unseal any of these secrets for someone. Now, if you use Windows, or administer Windows, you might say, hey, Microsoft has a BitLocker network unlock function. Why don't you just use that? And it's pretty messy. It requires some DHCP extensions. It requires a clear text EFI system partition. And it doesn't include any actual TPM signed quotes about the state of the machine, which eliminates one of the reasons for doing TPM sealing, because we only want this boot to happen if the firmware is correctly configured, that no one's gone in and modified any of the settings, or if they're some sort of local attacker who's either interposing things or rewriting the spy flash. So again, a lot of you are probably thinking, well, why don't you do remote attestation? And we actually have that for our Linux servers. You can watch my OSFC 2020 talk about the safe boot system and the safe boot attest for some more details on it. But what about these legacy systems that we have to support? And just to quickly run through some ideas that we had for how we could make our remote attestation work with this. We go back to the UEFI firmware loads from the spy flash. It then PXE boots a Linux kernel with some small, minimal, reproducibly built runtime that does our remote attestation based on the TPM quotes. And because the system is reproducibly built, we can validate the PCRs, send back the attestation secret. And in an ideal world, we could just kexec the NT kernel straight from there and then deal with the Windows update screen. In practice, this doesn't really work. You know, kexec doesn't support PE32. There's lots of undocumented APIs that the boot manager uses to hand off to the NT kernel. It's also very fragile to the Windows version. There is a project called Quibble that is trying to do exactly this, and they've reverse engineered the Windows boot manager to be able to exec the kernel. But again, it only supports certain versions. It's hard to upgrade, and Windows could break it pretty quickly, just accidentally. So another idea we had is boot from the spy flash, load our kernel, do our remote attestation, and then we could maybe kexec the boot manager as an EFI executable, which would then start the NT kernel. The problem that we run into here is that, you know, again, kexec doesn't support the right formats, and we don't have boot services support because we've called exit boot services inside that inside of Linux. One last idea, or another idea that we explored, is we have the reproducibly built environment, does the remote attestation, and then it instead kexecs the UEFI payload package, which is part of Tiano Core or EDK2 that has that's designed to be run as a payload under something like core boot, so that you can then run EFI applications underneath it. This then, in turn, could start the boot manager, which then starts Windows. And this actually works. This was a project that Chris Koch and some folks at Google worked on, and it works really well under QEMU, and it works really well on their systems because they have device drivers for all of the things that are in their machine. However, you don't get access to the real NVRAM and SPI flash because you don't have access to the real SMM. The UEFI payload package doesn't know about these vendor provided modules, so it's not able to take advantage of them. So what we finally ended up doing is, again, we boot from UEFI, we PXE boot our kernel, we get our remote attestation, and then we have a program we wrote called chain load that returns to UEFI, which then can load the boot manager either from a RAM disk or from a real disk, which then can start the Windows kernel from the BitLocker volume. And we're able to pass the BitLocker encryption key to that through that RAM disk. This lets us take advantage of all of the OEM device drivers that are in the vendor firmware. We get real NVRAM access because we have the SMM modules still present. But the key thing is that Linux can't disturb any of the UEFI state while it's doing this. So here's a quick demo of booting in QEMU, but this does work on real hardware. It's just, as Brian pointed out, real hardware takes a long time to start up due to stuff, memory training and things. So in this case, we start up QEMU, and we also start an attestation server in the small brown window. we pixie boot, our kernel starts up, gets some entropy. It then gets the attestation. We see the response come into that brown window. And then it kexecs back through chain load. And then in a second or two, there we go, we get the little Windows spinny thing. Yay, and we have Windows. So we can, we should be able to, there we go. So let's talk a little bit about sort of how we've been able to make this work. The first thing is that we have what we call the safe boot loader that is a signed kernel, initRD, and command line that we unify into a single PE32 executable. We sign it with SB tool, and this means that it's acceptable to the platform key that we have loaded into our server's firmware. So this means we integrate with UEFI Secure Boot. The next step is we have a wrapper around the kernel that is similar to the EFI stub from systemd, with a few exceptions. The first of which is it allocates, in this case, I think, half a gigabyte of memory, and it finds a 1 gigabyte region, excuse me, a 1 gigabyte alignment where it can map that. And that alignment comes in later because of page table things. It then adds to the Linux kernel command line a mim-map exact map, which says to Linux, this is the only region of memory that you're allowed to write to. So this prevents Linux from stomping on any of the UEFI data structures or any of the interrupt tables or things like that. We do have to map a small amount at 0 due to the SMP trampoline, which we shouldn't need because we're in a non-SMP mode, but that's an implementation detail. We also store a bunch of x86 cruft. Some of you may be familiar with the IDT, GDT, LDT, and things. We use those because we need to be able to return to UEFI, and it expects all of those values to have their original value. And then the other key thing is this Linux kernel does not exit boot services. Because exiting boot services is a one-time thing. That when you call that, it shuts down all of UEFI boot services. It also then remaps the runtime services into your virtual memory area. Linux can't call this because Windows is going to want to call it to map the runtime services to where it wants them. Windows also uses the boot services in its startup, so we have to leave these boot services running while Linux is running. The other thing is that we don't want to touch ACPI or PCI or any of the EFI structures themselves, which means we have no Linux device drivers. But you saw that we talked to the NIC, we talked to the TPM, we talked to the disk. And we did that by wrapping all of the UEFI device drivers through their protocol blocks. And this may come as a bit ironic to those of you who have seen my other talks, such as on Linux boot, where I made fun of UEFI device drivers and their code quality and things. But, you know, these things happen. And in this case, we want to work on commodity hardware, where Linux boot is about working on more customized hardware. So it's a bit of a compromise, but it also lets us boot Windows. So one of the first protocols that we wrap is the simple network. And this is a very straightforward blocking device driver that says, here's a packet, please put it on the wire, or do you have any packets for me? So we have something that wraps the Linux kernel skbuff and calls the UEFI transmit method to put that packet on the wire. To receive packets, we've got a bit of a hack because we actually don't support EFI events right now. Instead, we have a timer that's running that I think 25 hertz just checks to see if there are any packets. It's boot time, who cares? Performance is awful. We also have support for the UEFI block IO protocol. So all of the mass storage devices in the system show up here. And it's not just USB and regular disks, but on things like those servers, the RAID controllers also, through the UEFI option ROMs or Dixie modules, will show up as block I/O devices. So we can read and write from all of the disks in the system through this. And this is, again, a very simplistic model. It is a blocking API. So we have to use all of the Linux kernel queue scheduling things, but then we just block and say, as soon as we're done, we are done with this request. Again, performance is awful, but hey, it's boot time. Another fun protocol that we wrap is the EFI RAM disk. And this is what allows us to pass the secrets for the BitLocker encryption key to the Windows kernel. That we're able to mount or instantiate and mount a RAM disk, populate it with that key. We can also populate it with the Windows bootloader itself, which means we don't need any clear text at all on the disk whatsoever. And right now, when we instantiate it, it shows up as yet another UEFI block device. So we can run makefs on it and then mount it. And then in the case of the remote attestation example, we just copy the results that we receive from the attestation server. Another interesting module we've wrapped is the UEFI boot services start image method, which allows us to load new Dixie modules because most vendors don't actually package the UEFI RAM disk protocol. So we have to build our own Dixie module, put it in our Linux kernel, and then load it into UEFI so that we can then pass the secrets to BitLocker. I'm not sure why they don't support it, but this basically gives us a sort of like a mod probe that allows us to instantiate them. This does, because we go through the UEFI start image, this does actually end up getting measured and show up in the TPM event log. So we are, good citizens in terms of that, because we want to do accurate attestations. So speaking of the event log and the TPM, we also wrap the TCG2 protocol, and we actually don't use any of the methods with the exception of the submit command, which allows us to take the commands that we receive through dev TPM0. We just pass those directly through to the UEFI driver, which hands them to the TPM. And this means that we work out of the box with TPM2 tools without requiring any hacks or modifications to the user space. We do have some hacks, however, around the TPM event log. There is a bunch of messiness in the way the event log works. You can only read it before you call exit boot services. But calling exit boot services adds entries to the log. So the Linux kernel has a bunch of hacks at startup where it copies the event log, calls exit boot services, and then synthesizes the events that it knows should have been added during that process. It is an enormous mess. And in our case, we actually sidestep it. Since we don't call exit boot services, every time we cat the sysfs file, we actually just go query the TPM event log and say just, and copy it out. Again, performance is not wonderful, but hey, it's boot time. Now, a lot of you who have done hacking in this space might be saying, hold on, Trammel. Don't the UEFI boot services expect a linear memory map? And yeah, this is probably the grodiest hack in the system right now. And I'm certain there's a better way to do it, but this is an expedient way to add a map into the kernel threads that are then going to call the boot services. So in this case, because we know that the Linux kernel is on a 1 GB boundary, that means we can poke at all of the other entries in the top level page table, because they're 1 GB entries each. And as long as we skip the one that has Linux in it, we will remap all the rest of physical memory in that linear fashion. Again, this is really bad. I am absolutely positive there's a better way to do it, but I'm not a Linux kernel hacker, and I would love to hear from some folks about how to actually do it. But until then, this only lives for a little while, and then it kexec's something else, so who cares? The last part of the system that sort of ties together a bunch of these things is the safe boot attest. It brings up the network. It actually kind of clever. When the Pixie boot happened, the Pixie boot Dixie driver recorded the DHCP address that it received, and we're able to actually just reuse that. So we actually skip another DHCP request, but we're able to bring up the network, get the TPM event log, get a signed quote, send it off to the attestation server, receive that back, and then unpack it and populate the RAM disk with the result. Excuse me. Yeah, and then we pass the pass that result through the RAM disk to the to Windows, which we then chain load into the bootloader. And this chain load tool, it uses kexec, but it's not actually kexecing something new. It's taking the saved context for UEFI, so that GDT, the CR3, the LDT, IDT, and restoring them, and then returning to UEFI to say, this Dixie module has exited, and please boot whatever the next thing on your list is. And in this case, because we've set a boot next variable to point to the boot EFI Microsoft boot manager.efi, that is what then runs next, and then hello Windows 10. So, what's next for the project? We need to test on a lot more hardware. One of the goals here is that we should be hardware agnostic. That we should, because we don't have any device drivers in the Linux kernel, we don't depend on what kind of disks you have or what kind of NIC or what kind of graphics card. So it should just work out of the box. However, I suspect in practice we'll probably find that maybe we're not saving the right context for your hardware. Maybe your device driver is doing something weird with interrupts, and we need to figure out how to correctly map the IDT or to forward interrupts over to it. There are new legacy systems being invented that we might want to try to support. I don't have any experience with those, and the folks I'm working with on this project don't have any plans to move to Windows 11, but some of you might. I'd like to come up with a lot more flexible policies in the way we work with the TPM. We are working on trying to support encrypted commands to avoid some of the active interposer sort of attacks. But it's actually a pretty hard problem because you need a place to store secrets to establish that communication securely, but the TPM is where you want to store those secrets. So there's a chicken and egg for how best to make use of it. And another kind of fun application for this sort of system is as a installation environment, that if you want to make a install DVD for a system and you don't want to have to bundle every possible NIC driver and every possible graphics card and every possible hard disk driver, you could actually use this as the boot kernel for your DVD installer. And then it's able to use all of those devices to either fetch updates or to write to the disk and install things. We would probably want to improve the performance in that sort of case because then it would be a little more critical. But it's a kind of an interesting idea to avoid the need to bundle all of the proprietary drivers, especially for a free software distribution like Debian that doesn't want to put encumbered Wi-Fi blobs on their install media. In this case, you could boot a completely open kernel that can use those closed source drivers to fetch and download the rest of its installation. But the real sort of next step, and this is where I would love some help from folks who do more Linux kernel development and who are more involved in the community, is right now we would love to get the exit boot services patch into the kernel. And this UEFI device driver wrappers, just like we have the EFI stub and we have the EFI runtime services in the kernel, it'd be really nice to have these sort of things in the main line. Not everyone's going to use it, but it would be nice to have it in a clean, supported sort of manner. So this is how we're attempting to safely boot Windows with Linux. And thank you all for your attention. I'd love to answer any questions you might have.
Excellent presentation, thanks. We can talk about the exit boot services on the kernel side afterwards, not calling them. This is a problem that's going to keep increasing though, right? Because you skip the call of exit boot services now, but recently on recent kernels, we also measure the initramfs and we measure the command line. So depending on which PCRs you use to seal the BitLogger image, you might end up with different values or you might have to factor those in, right?
Certainly, the things that get measured are going to change depending on what path we take through the boot flow. Right now, the kernel, the initRD, and the command line are all measured by the PXE loader. So from Linux's perspective, there's nothing to be measured. But if we came in through a different path, you're right that we would have to take that into account.
So that was the reasoning on the kernel, right? We tried to get away from bundling everything together as a P binary and measuring one thing and thinking where everything is fine. So before we load the kernel, while the boot services are still up, we're measuring, again, initramfs and the command line, hopefully soon.
Right. And that will be super. That in the Safe Boot project, because the initRD is not measured by default,
exactly.
That's one of the reasons we switched to the unified kernel. The other reason to use the unified kernel is that it allows us to have a single signed PE executable. That if you have the separated ones, we would have to do signature checks in the kernel of the initRD.
And you don't have that, right? You can only measure it. That's the reasoning we measured it, because it's difficult otherwise. Thanks.
So what do you think about doing the UEFI service calls from, for example, user space instead of doing kernel drivers?
So making the boot services calls from user space would work just fine as long as you're willing to accept that you have no memory protection, which again, hey, it's boot time, why not?
Right. So I was thinking that for example, UEFI has a fetch HTTP service, right, with HTTP and HTTPS and stuff like that. So maybe you don't have to do the whole network stack.
Oh, interesting. That is an interesting idea to use the UEFI HTTP. That would allow us to remove curl, for instance, from the initRD.
Right, which is obviously the biggest security problem in this whole thing, right?
Yes, exactly. So I think it would be very interesting to think about what other things could we sort of move into a library and expose to either user space or to kernel space. And the HTTP is definitely an interesting one.
Hi, I'm not the biggest fan of UEFI, but since you're using it anyway, why don't you just write this in C as a UEFI app?
Excellent question. Why don't, in fact, in a previous version of the talk I had, why don't we write this as a UEFI application? And I had a screenshot of some UEFI code, and it is non-ergonomic. And I think Ron has a wonderful quote about Linux boot and things like that turn all of your Linux engineers into firmware engineers, and this allows people to develop things for the Safe Bootloader or for these other sorts of interfaces with shell scripts, with Go programs, with the tooling and the debuggers that they use every day, and asking people to try to write complex code in UEFI to replicate all of those things where they don't have the libraries, they don't have the tooling. It is a really big ask, and it would reduce the pool of available developers to a small handful instead of all of our Linux developers.
Yeah, I have a question. So actually you said that we cannot use ACPI in kernel. I wonder why. So actually drivers in the kernel, all they need is properties from this ACPI, right? And to make device drivers working, we don't need to modify it, correct?
So as not a Linux kernel developer, I'm not sure what went wrong, but when Linux touched ACPI, things broke. I believe that Linux, when ACPI was turned on, I believe Linux was trying to tell SMM or whatever that it had taken control of the power management. And I believe doing that prior to the exit boot services was causing bad behavior. However, I'm not certain. And again, since UEFI is still handling the power management and the thermals during this short period of boot, it seemed like a reasonable trade-off just to not do that. But if there's a reason that we should allow ACPI calls or ACPI table access during the bootloader, I'd be interested to follow up on that.
Yeah, I think it's something to consider. Maybe it will be easier. Yes. Thanks.
Okay, if there are no more questions, then thank you, Trammel.
All right, thank you all.